All right, section 4.5, exponential and logarithmic equations. Should go quick and smooth, I hope. So we're going to look at exponential equations, logarithmic equations, and we're going to revisit compound interest. It'll be the same formulas that we used before, but now that we have logs, we should be able to answer different kinds of questions using the same formulas. So we'll revisit some of those. Okay, exponential equations. An exponential equation is one in which the variables occur in the exponent. Some exponential equations can be solved by using the fact that exponential functions are one-to-one. So this means that a to the x equals to a to the y implies that x equals y, right? So if we know that, just to put some numbers on there, 3 to the power of x plus 2 equals to 3 to the power of y plus 3. Because they both have the same base and because they're equal to each other, this little property is letting us know that we can conclude from here that the exponents must be equal to each other. X plus 2 must be equal to y plus 3. Right? That's what this little thing is letting us know. Exponential functions with the same base. Good. So that'll be a useful tool to be able to solve a lot of exponential equations. Good. So as a general guideline, when we approach exponential equations, we want to isolate the exponential expression on one side of the equation. We want to take logarithms of each side and use the law of logarithms to bring down the exponent. I also refer to this sort of as the definition of logarithms, and then solve for the variable. Okay, so we'll kind of explore what all those things mean in this first example. So consider the equation 3 to the power of x plus 2 equals to 7. Part A, find the exact solution of the equation in terms of the logarithm. Part B, use a calculator or technology to find an approximation to the solution round to 6 decimal places. Okay, so part A, let's find the actual answer. Part A, we have 3x plus 2 equals to 7. Well, one thing we could do is rewrite this as a an exponential number with base 3, and we'll leave that as a plan B. We'll come back to that. But for now, what we'd like to do is apply a log to both sides of the equal sign. Right? The reason we want to do that is because one of the really important properties of logs is that is the one where we have this one. If we have log base a of any number raised to the power of, say, I don't know, w, like this, equals to y, say something like this. One of the properties, and in fact we don't even need the equals y. One of the important properties of logs is that it lets you bring this exponent that's up here, this guy, it lets you bring it out in front. We can say that this whole thing is equal to log base a of x multiplied by the w out in front here, like a linear factor. Right? So it lets you bring that exponent out in front. Here, the unknown variable that we're trying to solve for is up in the exponent. And this property is the only thing we know of that allows us to get it out of the exponent and be able to solve for it. Right? There's nothing else we could do. We cannot divide by 3, multiply by anything. We can't add or subtract anything. There are no other operational symbols or operations that we know that would allow us to simplify this except for this. Good. Okay, so we got to apply a log to both sides. We're allowed to do that as long as we maintain the equality of the equality. We could do whatever operation we want. So we choose to apply a log to both sides. Now you can apply any log you want as long as you're applying it to both sides. So as long as you're maintaining that equality, you can apply a log to both sides, and you can make it, any index you want. We can make both of these 8 if we want to, log base 8. That's fine. Or we can make this log base 13 if we want to. Sure, pick your favorite log. However, why not make life easy, right? There's a nice easy button in our calculator for log base 10, so why not use log base 10? So log base 10 is a very popular log to use, right? Likewise, it could be any log. Another very common, very easy log to use, I'll put it over here, or, and as long as the stylus is working, let's do this. We can say ln. ln is another very popular log that could be used, right? It's log base e. Either way, let's just keep going. It's a fairly simple example. Okay, so now we get to bring the exponent out in front like a linear factor. So we're going to be able to bring this guy out in front. And same with this guy, we get to bring it out in front. Good. We'll solve both of them side by side. We have x plus 2. And then we have log base 10. And then if it's log base 10 by default there, then you just don't write anything. Just makes it easier. And then log of 7. right? By default, if there's nothing written there, we know it's log base 10. And it's really annoying in some parts of math where they don't write anything, and by default is the exponential one. So be careful with that. When you move forward into some other field, some of the engineering fields and stuff, I'm pretty sure electrical engineering, I've seen some of their graduate work. I saw some formulas, and somebody asked me to help them figure out what they were doing there, and it stumped me for a really long time. I kept staring at this thing saying it's base 10, and it was just bugging me, and eventually it occurred to me that they meant log base e, and they just wrote it this way, and it was meant base e. So anyway, just be careful. I think some of their fields take slightly different notation, right? It's one of the big hurdles of science, notation. Okay, so next what we're going to do is we're going to divide both sides by this. Let me write it down. So next we're going to divide this side by log of 3. Divide this side by log of 3. We're allowed to do that because this is a number, right? Remember, we're not allowed to divide by log. That's a mistake people make very often. They see log of 3 and they divide by log, and somehow the logs cancel, so this equals to 3, right? That's not true. But we can divide by log of 3. Right? This is a decimal. It's the decimal such that 10 to the power of this number equals to 3. Good. So some decimal value is represented by this notation, and we can divide both sides by that decimal value, which would result in x plus 2 equals to log of 7 divided by log of 3. Good. Now we just subtract 2 from both sides, and we get our final answer. X equals to log of 7 over log of 3 minus 2. Any questions about that? No? Okay, so there was nothing special to log base 10. It's just an easy button on my calculator, so why not use it? But likewise, ln is popular, so we could just solve it using ln, and it's going to be the exact same process. You get to move the exponent out in front like a linear factor. Get that page number there. So this is x plus 2 ln 3 equals ln 7. Divide both sides by ln 3, so x plus 2 equals to ln 7 divided by ln 3. Oops. And so x equals to ln 7 divided by ln of 3 minus 2. Good. Again, note that log base 10 of 7 does not equal to ln of 7, and log base 10 of 3 does not equal to ln of 3. However, the ratio of these two, the division of these two, will be equivalent to the division of these two. So you get the same answer either way. So another approach to this thing would be to use graphs. Okay, I think that's what they wanted you to do for part B, right? Use a calculator to find the approximation of the solution, round to 3 decimal places. So we can use graphs to solve it, and we'll do that next. And then that also opens up another idea of how to solve this. That would require some graphs to do it. Okay, so then let's just type this into our calculator, get an answer, and then check it. It's important to always check your work with these guys. So using my easy buttons, I have log of 7 divided by, oops, clear. Log of 7, close parentheses, divided by log of 3, close parentheses. That's going to give us some answer. This thing's way too big. Oh, that's too small. So log of 7 divided by log of 3 is going to give me some answer, that decimal. And that decimal is going to be the same as ln of 7, close parentheses, divided by ln of 3. ln of 3. Either way, we get the same decimal. And now that decimal gets subtracted by 2. And we get that value, negative 2288, rounded to 4 decimal places. Good. And so we check it. Going back to the original statement, let's see if that's the number, that's the value that solves it and gives you a true statement. Is it true? Check. Is it true that 3 to the power of blank plus 2 equals 7, where that blank is this negative 0.2288? So that would be minus 2. So that would be 3 to the power of 1 0.81, 77, 7712, right? 2 minus 0.2288, 2 minus 0.2288, 7712, yep. 7712 equals 7, potentially, hopefully. And then we check that in our calculator. So 3 to the power of 1.7712. And yeah, it's pretty close. Okay, now using technology to solve it. We have, this is a very useful trick. Now, there's very few things that you're actually going to use in any of your classes moving forward, right? That's not what we do here. I'm not really teaching anything useful or valuable, sorry, or for the most part. But there are some little tricks that you actually use a lot, and this might be one of them. And we use it a lot in math as well, in this class and in calculus. And I think in a lot of the engineering classes you take, this kind of trick might be useful. Unless you're allowed to use computers to solve things, and then this trick is just kind of silly. But if you get to use a calculator and you have to solve an equation, then this is a useful trick. So solve this. Well, we've found one way to solve it, logs and bring the exponent and do all that stuff, okay? The other thing you could do with your calculator is to rewrite this as one function. Here's one function. We're going to call that y sub 1 in our calculator. And then the other side is the other function, and in this case, the other function is just 7, right? So we're going to have y sub 1 equals to 3 to the power of x plus 2 as on your calculator, right? This is a function. And then for y sub 2, we're going to have just 7. Good. So this is the function f of x equals to 3x plus 2. So this is an exponential equation base 3. When I graph this, we'll use our calculator, but just in general, without any actual numbers, just to kind of conceptually see what's going to happen. This equation is just going to have some sort of thing like that, maybe. Okay. And then this equation over here is this one. It's just the line y equals to 7. It's just going to be something like that, right? And we want to know, when do these two things equal each other, right? So here is 3 to the power of x plus 2. That's this equation here. And we want to know this. When do they intersect? At the place they intersect will be our solution x, the one we're looking for, the place where this works. Good? Questions, 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 questions? Okay, so let's do it with our calculator. So we want to go to y equals, clear old things. So we'll have 3 to the power of parentheses x plus 2, close parentheses. Let's just graph that guy for now. Let's go to window. And from 0 to 20, let's go from -5 to +5 and see how that goes. And outputs, I don't know, let's go from negative 20 to positive, I don't know, 100. We can always come back and change this to see if it see how it affects things. So there's my exponential function. Good. And now, if we graph the y equals to 7, there's that line. Okay, well, it's kind of hard to see way down there. So now I can go back to my window and just kind of focus on this guy. Now I can see that it's just really close to down here. So let me go to my window. And instead of -5, let's go from -2 to +2. Just kind of narrowing in on the input side. And the output side, I don't know, let's go from -2 to +10 maybe, and see if that does a good job of narrowing in on it. Ah, there we go. Okay, so I found out where that intersection was. And remember that where they cross is my answer. The input, the x-coordinate of the intersect point is going to be my solution. Good. Okay, so let's see. So then now if I go right here where it says calculate, right above the trace button, calculate, second, calculate, and then I want to go down to intersect. Intersect, hit enter. And now it's asking you for the curvatures. So there's only 2 equations on there, so this should be easy. Just hit enter once, hit enter twice, since there are only 2 of them. If there was more than 1 equation on there, like let's go back over here. Let's throw in another random equation onto here. I don't know, x equals y equals x, for example. Just another random graph on there. There it is. So now when I go to the calculate intersection, it's a dumb calculator from the 80s, 80s technology here. So if you go up and down, it'll let you scroll through the 3 different equations I have. So that when you want to find the intersection, it wants to know which 2 equations would you like to check if they intersect or where they intersect. So you can just hit enter to select it, and then you can toggle between the others so you can get to the one you want. So right now it's blinking on that one, and that's what the one I want. Hit enter. And then it says guess. So you can go left and right and travel across one of these functions until you get to a pretty good guess. Now again, there's only one place that these two cross, so it's kind of a silly question. But if it was a more complicated curvature, you know, like a cosine up and down, and another line through it, there might be lots of places where the graphs intersect. So then, in that case, it would be a little bit more appropriate to ask you which intersection you're talking about. But anyway, so we guess, we get pretty close to it, enter, and there's our solution. The x-coordinate of the intersection is going to be our solution. Good. So that's how we can use our calculator to solve it. Well, we can do a similar thing with other technologies, the graph, like Desmos, graph both equations, figure out where they intersect. So this is generally a pretty useful tool whenever you're trying to solve any kind of equation that's really complicated. There might be a really ugly thing on the left side, there might be a really ugly equation on the right-hand side. As long as they're functions, as long as both sides are functions, then we can write in a function on the left-hand side, a function on the right-hand side, graph them, see where they intersect, and all the intersection points are solutions to the original equation. Any questions? Oh, my sketch was way off then because they cross over here, right? But this was just sort of in general. Questions, 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 questions? No? None? None? Okay, let's see what the author did. Very similar, applied log to both sides. And then divided, yep, same thing I did. Yep. Check it, okay. Oh, they didn't, using a calculator we find the decimal approximation to be equal to this. Oh, for part B they meant use a calculator to convert this into a decimal. That's what they meant by use a calculator to find an approximation to the solution rounded to 6 decimal places. Okay, I interpreted this wrong. They just meant to convert your exact solution into a decimal approximation. I thought they meant starting from scratch, starting from up here, use technology to solve it, which is what we did. Oh well, we went over a very useful calculator trick to help you. I wouldn't say it's a trick, it's just a useful way of solving equations using a graphing calculator. Whoops, why is it giving us the answer? Okay, okay, this is broken. It just wants you to solve this, and I don't want to sneak down here and show you the answer, so I'll just write over here. Solve e to the 2x minus e to the x minus 6 equals to 0. Okay, so it's an exponential equation because the unknown variable that we want to solve is up in the exponent. It's not quite as easy as before, where we just applied a log to both sides and we're able to bring the exponent down. Remember that that property only works as long as we have something that fits this form, log base a of x to the w. If we have one exponential number like this inside the argument of a log, that's when we can bring it out and say that it's equal to w times log base a of x, right? No variations on this. Don't make up your own way of this working. There's nothing in our properties of logs that says that if we have this x to the second plus x to the y plus 9, that you can do anything that involves just bringing these exponents out, right? And also we don't have a way of separating this into the addition, log base a of x squared plus log base a of x to the y, right? We don't have that. We can separate it if there's multiplication in here. We can separate it into the addition of the addition of logs if the arguments in here are being multiplied. And we can also rewrite it as a subtraction, as a difference of logs, if the argument inside here was a big fraction. We can do that. But if we have addition or subtraction inside the argument of a log, we're out of luck, right? Those properties do not work. And also, we're not allowed to bring this 2 out in front, or this y, or rewrite this as a 3 squared and bring out the 2. Right? We can't do any of those things. So none of that is helpful right now. So what we have to do is realize that this one is a quadratic in disguise. Right? This is e to the x squared minus e to the x minus 6 equals 0, right? So now we can do a simple u substitution. Let u equal to e to the x. Okay. So then, in fact, you know what? I'll give it to you in color. About blue. Let u equal e to the x. So we're going to have a u here, and then another u. And this is squared minus u minus 6 equals 0. So now it looks like a quadratic, right? And it should be a straightforward quadratic. It should fit this form. Two numbers that multiply to -6 but add to -3. I'm sorry, add to -1. So that should be -3 plus 2. u minus 3, u plus 2. They multiply to negative 6, but they add to negative 1. Right? And then now that we've realized how to factor it, now we can come back and replace the u again with an e to the x power. E to the x minus 3, e to the x plus 2 equals 0. Good. Because we have a product equals 0, we have a multiplication here of two things, two binomials in this case, that multiply to 0, we can use the zero product principle to separate this into two pieces. Either this part must be 0, or this part must be 0. Good. Add 3 to both sides, we get e to the x equals to 3. E to the x equals to 3. Okay, so now we can apply a log to both sides. We can apply any log, but in particular, why not apply ln? ln e to the x equals ln of 3. Good. And then one of the properties of logs is that these two are inverse operations. ln of e to the x, this thing, these two operations undo each other, and this just becomes x. So we get that x equals ln of 3 as one of our solutions. Over here, we do the same thing. We subtract 2 from both sides of the equal sign. Minus 2, minus 2. And so we get, e to the x equals to negative 2. And that should be where we realize that that is leading to a dead end. Right? Remember that the graph of any exponential function where the base is bigger than 1 is going to have this sort of a shape like this. Right, this is a to the x power, where a is strictly greater than 1. Good, 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 good. And if a was a value between 0 and 1, it would have this sort of shape that comes this way. Oops. It would have this sort of a shape that comes this way, like that, if a was trapped between 0 and 1. Either way, the outputs are never, ever, ever going to be negatives. Right? So the output, the answer to an exponential number like this, is never negative. So this is no solution. So the only answer we have is x equals ln of 3. Now we can leave it like that as an exact answer. Or again, we can use our calculator to turn it into a decimal approximation. And if we turn it into a decimal approximation, then it becomes easy to again use our calculator to check and verify that in fact this is the right answer. So you just type that in your calculator, ln 3. I'm getting x equals to, oops, which color now? I'm getting that x equals to 1.09861. Let's just leave it at that. Good. So now let's check it. Is it true that e to the power of twice something minus e to the something minus 6 equals 0? Right? Where that something is this decimal. 1.09861, 1.09861. So it's just a matter of typing into our calculator and confirming that it does give you a true statement. Good. Let's check it. I'm going to check it real quick here online. Check it on yours. Oops. 2 times 1.09861 e to the power of that plus, minus e to the power of 1.09861. Yeah, getting pretty close to 0. Any questions? True. No? Good, 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 good. Okay, let's see what the author did. Same thing. This is a quadratic in disguise, so we can rewrite it this way. They didn't bother with a u substitution, but I did. I wrote this u substitution. And then that gives you this, which gives you that. No solution for this side, and there's only one solution for that guy. And then he didn't do the check, but plug it in, you check, and you see it works. Good. Any questions? Okay, logarithmic equations. Logarithmic equations are going to be similar. We have equations we're trying to solve, and we get to use logarithms as a way of solving them. And we want to be able to apply this statement here, that if an equation has, say, log base 7 of something, happy face, is equal to log base 7 of something, sad face, well, whatever these are, they must be equal to each other, right? They both have log base, the same index, right? So this property is saying that they must both have the exact same argument. That must mean that this is equal to this. Mustache. Okay, so guidelines for solving logarithmic equations. Isolate the logarithmic term on one side of the equation. You might first need to combine logarithmic terms, so we get to use our properties to contract or expand logs. In this case, we'd like to contract them into one big happy log. And then we might use the definition of logs. We might get to apply this property where we apply log to both sides of the equal sign. So they vary a little bit, but we've got a variety of tools to help us. So here's a couple of examples. And for both of these, I refer to it as the definition of logs. Remember that if we have log base a of x equals y, then by definition, there's this little thing, this to that power must be equal to that, right? If and only if and only if it's true that a to the y power equals to x. If you forget that whole thing, just think of a simple example. So 2 to the power of 3 equals to 8. So that must mean that if we kind of go backwards, log base 2 of 8 equals 3. Right? Again, this little circle, 2 to the power of this guy must be that guy. Okay, so this might be might be helpful in remembering the property. Okay, so that's what we want to apply here. Remember, ln is log base e, so there's a little e there. E to the power of that guy must be this guy. And that's it. That's all you have to do for this one. E to the power of 8 is equal to x. This is just some number. I can just use my calculator to find it. Okay, this is just e times e times e times e multiplied by itself 8 times. Questions? No? Okay. So we can use our calculator. Okay. I'm going to launch it and see how it does. I try not to keep the program open because it slows down the stylus I've found. I have too many programs open. Let's quit from here. And so e to the power of, e to the power of 8 equals this number. 29, 80, 95, 80. 29, 80. 95, 8, approximately. Good. And you can check it to make sure. Check to make sure. Well, if it works, it must be the value such that ln of that number is approximately equal to 8. Right? So we can check it by plugging in that number right into here, going back to the original equation. And again, we can use our calculator to check that. 8. Okay, so if it's true, it must mean that ln of 2980.958 approximately should be pretty close to 8, and it is. A little bit of rounding issues. Any questions? No? We're good? Okay, this next one, same thing. We want to use this property that this little base to that power equals to this, right? It's the definition of log. A lot of people stare when they look at these. I feel like they just get stuck with this word. Their eyeballs just hit this right here, and they don't know what to do with it. They're trying to remember what is the definition, logs. They try and solve for L or something, like they're variables or something. Right? So you really got to get away, get past that and focus your attention. Your eyeballs should be focused on this little index right in there. Right? We know that this raised to that power must be equal to this. That's how we want to solve for whatever is inside the argument of the log. In this case, where we have one log equals something on the other side, particularly if that other something doesn't have any logs in it. Good. Okay, so applying that property, very simple. We get that this must mean that 2 to the power of 3 must be equal to 25 minus x. Good. All right, well, 2 to the power of 3 is just 8. 8 must be equal to 25 minus x. And now we just solve for this guy. Minus 25 minus 25 gets you to 17, so minus 17 minus x, and then divide both sides by that minus, so we get that x equals to positive 17. Good. Check. log base 2 of 25 minus x, oops, something, equals to 3. So check to make sure that 17 is the number that goes in there. And we'll use our calculator to do that. Okay, so that must mean that log base 2 of 8 must be 3. And, well, this is one of the obvious ones we already know. Log base 2 of 8 must be equal to 3. We did that over here, actually. Log base 2 of 8 equals to 3. Good. Definitely true. Okay, so they were just kind of conveniently easy numbers, but what if they were really ugly numbers that we didn't really know just by looking at them? Let's use our calculator to check it. So again, we're not solving it, we're just checking to make sure that this really does equal 3. Okay, so let's do that with our calculator. We got a couple of choices. For one thing, well, before I go there, remember we have this change of base formula, right? If we don't know that this equals to 3, it's just not off the top of our head, we don't know that that's true, and we want to find out what is this, remember that our change of base formula from yesterday says that we can convert it into any index we want, log base anything we want, by using the change of base formula, and so we can change it into something more convenient, like an ln function, ln of 8. I don't know what log base 2 of 8 is, so I can use ln of 8 and divide it by ln of the base that you didn't want to use, the index you didn't want to work with. So this division, this ratio, will be equivalent to this, right? And since we know the answer is 3, I'm saying that this will be the decimal such that e to the power of that decimal equals 8. This will be the decimal such that 3 to the power of this decimal equals to 2. But then when we divide them, I know that they're going to be equal to 3. Good. Let's check all that. Calculator. Okay, so ln of 8 equals that decimal, right? That's the decimal such that e to the power of that decimal, 2.07944, something like that. That's the number such that e to the power of that decimal equals to 8. That's its definition, right? Given some rounding issues, pretty close to it. Good. And then ln of 2 gets you to that decimal. So ln of 2, that notation represents the decimal such that e to the power of that decimal, 0.693147, that whole thing, it's approximately equal to 2, right? Okay, so now the numerator is 2.07944, this number, divided by 0.693, this decimal right here. The division of those two is going to be pretty close to 3. Right, so 2.079441542 divided by 0.69314718006. Pretty close to 3. Okay, well, we could have just saved ourselves a lot of the trouble here. I was just trying to point out what these decimals really represent. But really, we just type it all in one sweep. Ln of 8 divided by ln of 2. And we see we get an answer of 3. Good. Okay, again, as long as we're just checking what things are, there is a way for some of you to be able to figure out what log base 2 of 8 is directly. This won't be in every calculator, just some of the newer ones have the software for it. So the way you would do it is to go over here where it says math, this button that says math, and then you got to find the one that says log. And I don't know where it is exactly. There, log base. It says log base, like this. Again, so hit math, and then right here you get this menu, and under math you scroll down until you see log base. Like I said, most of you probably won't have this. Only some of the newer calculators have them. If you don't have it, then you're stuck doing it the old way, one of these other ways. Okay, but if you do have this, then you can hit enter, and see now it gives you a way for you to type in the little index of the log. So you can type in a 2 there. Go over, and then I can type in an 8 here, and then go over, and then hit enter. There. Okay, so here's a loose application of this stuff. So logarithmic equations are used in determining the amount of light that reaches various depths in a lake. This information helps biologists to determine the type of life a lake can support. So as light passes through water or transparent material, such as glass or plastic, or gases, right, an atmosphere, some of the light is absorbed. It's easy to see that the murkier the water, the more light is absorbed. The exact relationship between light observation and the distance light travels in a material is described in the next example. Okay, whoa, let's zoom in a little bit. So if I sub naught and I denote the intensity of light before and after going through a material, and x is the distance in feet that the light travels in the material, then according to Burr-Lambert law, we have this relationship is true, where k is a constant depending on the type of material. Okay, so 1 over k, negative 1 over k, ln of I over I naught equals to x. So I naught is the initial intensity, right, before it hits a surface, let's say the surface of the water, the intensity of light at the surface of water, and then it goes through a certain depth. Depth is x, so maybe 3 feet underwater, 10 feet underwater, 100 feet underwater, so the depth underneath. Capital I is the intensity of the light at that point, at that depth. And then k is some constant related to the particular substance we're talking about, whether it's glass, whether it's water, and even within water, there will be different constants for different types of waters, whether it's ocean water, whether it's freshwater lake, just how much sand is in there, how much pollutants are in there, stuff like that. So this sort of thing is also very useful if you're looking at like oil spills, and now it's not just affecting, there's a whole lot of things it's affecting, and one of those is the transparency of light. If the water is very polluted with all that oil, it's going to make it more difficult for light to make it all the way down to the depths it used to make it to, and then that will affect those organisms deep down there that are counting on that little bit of light that was getting down there. So anyway, so this is the property that applies. There was no explanation given as to where this comes from. So at this point, we're just expected to understand the formula, not really worry about where it comes from, and then apply it, use it, love it, and move on with our lives, right? So here's the formula. So here's an example. So for part A, it says solve for I, solve for capital I. So we have that negative 1 over k, ln of I over I naught equals x. So solving for capital I should be pretty easy. Ln of capital I over capital I naught is equal to kx, right? Multiply both sides by negative k. And now we want to use the definition of logs. Remember, this is a little e there. E as the index raised to that power must be equal to whatever's in there. So I can conclude that, let's go to that page, I can conclude that capital I divided by I naught is equal to e to the power of negative kx. Good. And now if I multiply both sides by I naught, I've solved for capital I. Capital I equals to I naught times e to the negative kx. Good. So that's the answer to part A. Solve for capital I. Okay, now for part B, for a certain lake, k equals to 0.025, and the light intensity is 14 luminance, I sub naught. So the initial intensity, when initially at the surface of the lake, is 14 luminance. Find the light intensity at a depth of 20 feet, so x equal to 20 feet. Make sure that the units match, and then up here, this thing was given in feet, the distance was given in feet, so that works fine. And then the light intensity was not was given in luminance. I think it's implied that light intensity is measured in lumens. Sorry. Good. Okay, so for part B, they tell us that I sub naught is equal to 14, and that x is equal to 20. So we have that guy, we have that guy. Oh, sorry, and that k was equal to 0.025. So then it just becomes a plug and chug kind of question. So one thing I'm pretty disappointed with this book about is the word problems are kind of easy. They lack imagination, and they focus a little too much on formulas that are unexplained. But do what we do. All right. Okay, so there's the thing we need to solve. We can just punch that into our calculator and get a decimal approximation. So e to the power of negative 0.025 times 20 equals that, and we multiply that by 14, and I'm getting approximately 8.5 lumens. Oops. 8.5 approximately. Good. So at a depth of 20 feet, so light was 14 lumens in the surface, 20 feet underneath the water. The light intensity is now only 8.5 lumens. Questions? Approximately 8.5. Light intensity at a depth of 20 feet is about 8.5 lumens. Any questions? No? Okay, compound interest. We've already explored these formulas. Remember that if we have simple interest, an interest rate, say a 1-year interest rate, and we want to find out what the balance is at the end of 1 year if it's compounded only once, then this is the formula. Now, it doesn't have to be a year. It's just that that's the most common way of doing this, because by default, interest rates in our society, at least, are always given in terms of a year. Whenever you get a credit card, whenever you get any kind of loan, whenever you buy a house, every interest rate is given in terms of an annual rate. It's just a way of standardizing it. Nothing special about that. The government could have just as easily mandated that all interest rates be given on a daily basis, your daily rate. And I think that would have been easier, I think. It would have been easier in concept. The problem is that the actual number you work with would have been really, really small. So you'd have a lot of zeros in there. Very easily made it every month. The interest rate is given on a monthly basis. It's just a standardization, just to make it easier for people to maneuver through our financial infrastructure. But it's not. There's nothing really special about it. Okay, but by default it's 1 year. So if we have interest rate given in terms of an annual rate for 1 year, then this is the formula for simple interest earned after 1 year. If, on the other hand, it's compounded n number of times per year, like maybe compounded monthly, compounded daily, the compounding, remember, it's the time when they do the formula, when they actually check how much interest is earned, and then they deposit the interest earned into your account, so that the next time it gets compounded, they give you interest on the interest earned the first time, right? So it's kind of like a maintenance thing. How often do they look into your account and do maintenance on it to add the interest you had earned, and thereby letting your account be a little bit bigger the next time they do maintenance on it, so that they can, again, have your interest earn interest, right? The secret to being super wealthy is just having a bunch of money, and then your money makes money, and then that money makes more money, and you just got to kick back and, have margaritas by the pool. Let your millions make more millions, and people think you're brilliant because you're so rich, you make so much money, right? Just got to have, a really rich daddy that gives you a couple $100 million. There you go, rich, you're smart, great businessman. At any rate, off that rant. And then we looked at compound interest. We got this formula for compound interest, right? And this means that it's compounded continuously, right? When we have a situation where the interest is compounded, not just every second, but every fraction of every second, continuously compounded interest, we'd have this sort of formula. In our financial system, we work with compounded annually very often. We work with compounded monthly very often. Credit cards like to compound monthly. That's when they do the maintenance, right? They check once a month. How much do you owe? Okay, let's charge you a fee for what you owe this month. And then if you don't pay any of it, the next month when they do maintenance on it again, well, now they charge you money on the money they charged you the previous month, right? Now the debt is earning more debt. Debt earns debt. Debt earns debt. So if you just ignore it, that could really blow up, right? That's the secret for them making a bunch of money and for people staying in debt. The fact that it gets compounded, right? Your debt generates more debt. Okay, so credit cards work very often on monthly compounding. The stock market likes to work very often on daily compounding. Every single night, large institutions borrow money overnight. They call those the pink sheets. So if anybody out there is interested in becoming a broker in Wall Street, and that's a really big market. That's people lend institutions billions and billions of dollars for one day, just overnight. The market closes today at 3 in the afternoon, and on computer, at least in their system, sometimes they would like to have a bunch of cash available to them, so they borrow it for one day, and then in that one day they pay interest on that, so they pay a daily interest rate. There's a really famous case you can look up. There's a bit of a rant, but there's a really famous case of a guy that worked for Bank of America, and I believe it was China that had borrowed a bunch of money from Bank of America, like billions of dollars. You can Google it and find the details. I'm really rough with details, but anyway, China borrowed a bunch of money from Bank of America, and then China was paying it back to Bank of America. And this guy was, high up in the ranks of a Bank of America, and he was involved in that whole computer transaction. So anyway, he arranged it so that China paid them back on February 28th, and then it appeared the next day on the Bank of America computer system that China had paid them back on March 1st, February 28th, March 1st, looks good, except that this happened to be a leap year, right? On leap years, we have one extra day, February 29th, which also happened to land during a business day that he could work with. So when China paid back the money, he fudged it, so he stole the money for one day and put it into the market so that he could lend it out for the one day and earned a bunch of interest. I don't know how much, probably hundreds of millions of dollars in interest, since it was billions of dollars that he stole for a day. He went over to the markets, to the pink sheets. This is all electronic. He went over the pink sheets, he borrowed, he lent out all that money, he made a bunch of money in interest, and then the very next day he put the money back that China borrowed back into the Bank of America computer systems. So he only borrowed the billions of dollars for one day and made hundreds of millions of dollars for the one day in the pink sheets. So daily interest rates, they're a thing. Would have been a great heist, except since everybody knows about it, he probably got caught then, right? Luckily, it's white-collar crime, so he probably didn't do much time or anything. They probably just gave him community service or something. Steal 20 bucks from a liquor store, you can get, years in prison. Steal billions of dollars for one day, and no community service. Maybe a light sentence. Anyway, man, I go on rants today. Let's look at some examples. A sum of $5,000 invested at an interest rate of 5% per year. Find the time required for the money to double if the interest rate is compounded in the following methods. Okay, so we know our formula for compounding. For this one, semi-annually, it's going to happen twice a year, so that means n equals to 2. Semi-annually is just going to be this formula. We'll replace n by 2. We know the interest rate, we know the principal, and we know that it's going to double. Okay, so let's look at our formula for this one. Go away. So the formula for this one was going to be that the balance in my account is going to be the principal 1 plus r divided by n to the power of nt. And for semi-annually, that means that n equals to 2. And we know that p equals to 5,000. And we know that r equals to 0.05. And we're looking for t, find the time it takes for the principal to double. So I know that the output of this thing should be twice the original principal amount, twice p, right? So it should be equal to 10,000. Good. Okay, so we can replace these values in here and get this statement. We're looking for the value of t such that 10,000 is the output when 5,000 is invested, and we have 1 plus 0.05 divided by 2 to the power of 2t. Good, so now it's just one little letter that needs to be solved. Let's simplify life. Let's divide both sides by 5,000. Divide this side by 5,000. And so we see that this is just going to be 2. 2 equals this thing. 1 plus 0.05, well, let's just change it to this is just going to be 2.5%. 5 divided by 2 is 2.5%. And then you add that to 1, so it's just going to be equal to 0 to 5. 2.5%. Raise to the power of 2t. And now, the thing we're trying to solve is in the exponent, so that means we have to apply our log functions to solve this. So I'm going to use log base 10. Log base 10 of 2 equals to log base 10 of 1.025 to the power of 2t. Right, so now that means that this exponent gets to be brought down like a linear factor, and I'll end up with 2t times log of 1.025 and then log of 2. Divide both sides by this log, and 2 and we solve for t. So divide by 2, log base 10 of 1.025. Divide this side by 2 and log base 10 of 1.025. And then we solve for t. So t is going to be equal to log base 2 divided by 2 times log base 1.025. Good. Okay, so now we get our calculator and check that. I would start with these two, and I guess I can also separate it as being times 1/2, the product of that division. Anyway, different ways for you to type it in. So log of 2 divided by, and then in parentheses I'm going to put 2 times log of 1.025. Close parentheses, and 14.03551. 03552. Okay. Questions? You can check. Is this true? Is this how long it's going to take for it to double? Okay, remember it was 5,000 times 1 plus 0.05 divided by 2 to the power of 2 times t. Right? We're going to check. And if this works out, if it's true, then it must mean that this whole thing equals to 10,000. Oops. That this whole thing equals 10,000. Right? It's the time it takes for your initial investment to double. Okay, so we can just type that into our calculator and check it. So 2 times 14.03552. So that's that product. And I want to say 1.025 to the power of that previous answer. I'll use this previous answer. To the power of 28.0704 times 5,000 gets me 10,000. Right? Pretty close to the answer I was expecting. Any questions? No? No? How do we turn this into a more appropriate way of saying, a more, we don't like to say decimal number of years, or it doesn't seem as palatable. So think of this as a percentage of the following year. It's 14 years, and then it's 3.55% of the following year, which we can turn into number of days. So if you take the 0, if you take the 0.03552 and multiply it by 365 days, there we go. 0.03552 times 365, I get approximately 12.96. We'll just round it to the nearest whole day. That's 13. So 14.03552 years is the same thing as 14 years and 13 days. I think sounds a little better than just saying 14.03552 years. Good? Questions? No. Okay, so this was for it being compounded semi-annually, right? Just every 6 months, they're going to do maintenance on your account, figure out how much interest you've earned, deposit it onto your account, so that the following time that they do maintenance on your account, 6 months after that, now your interest you earned the first cycle also earns interest. You're going to earn a little more. So the speed at which you grow your investment is going to go a little bit faster when you compound it more often. And so when you get to the point where you get to compound it continuously, then we use this other formula, right? So compounded continuously would be this formula. Okay, so P equals to e to the RT. Sorry, P equals P RT. A of t equals to P times E to the RT. I don't know where I got P equals. Anyway, and so we have all the values we need here. We know R, we know P. We're looking for T. And we know that it doubles, right? So here, this will turn into 10,000. The investment doubles. And P is still 5,000. E is a constant. It's the power of 0.05 times T. Divide both sides by 5,000. We get 2. Divide by 5,000. Divide by 5,000. These guys cancel. We get 2. 2 equals to e to the 0.05 t. Apply ln to both sides, and we end up with ln of 2 equals ln of e to the 0.05 t. These two operations are inverse operations. They undo each other. So on the right-hand side, this just drops to become 0.05 t. ln of 2 equals that. And so if we divide both sides by this decimal, we get divide this side by 0.05, divide this side by 0.05. These cancel, and we're left with t is equal to the division of these two values, ln of 2, 0.05. Good. So again, we can just use our calculator to find a decimal approximation. So we want ln of 2 divided by 0.05. So I'm getting 13. Oops. 13.86 something. 8629. 13.8629. Good. And again, we can check it by going back to our description. Is it true that 5,000, right, check. Why does it check with two C's? Check. Check that 5,000, the initial investment, times e to the 0.05 times this number, that this whole thing really will be equal to 10,000. I'm pretty sure it will. Any questions? No? So compounded continuously, the account will grow to will double in 13.8629 years. So that doesn't seem quite so easy to understand. Again, you can think of this as 86.29% of the following year, but people like to see things in terms of months and days. So let's do the same thing as we did before. So I'm going to multiply 0.8629 times 12, because there's 12 months. Right? And when we do that, you get 0.8629 times 12. Right? This equals 10.3548 months. Right? So 0.8629 years. 0.8629 years is equal to 10.3548 months. And now this is the percentage of the following month, which has 30 days. So 0.3548 months, right? This is in units of months, times approximately 30. And I know every month is a little bit different. It adds to the complexities of our silly calendar. I don't know if you ever thought about why we have such a silly calendar, but we do. This one is 10.644. Right, so now this is days. Okay, so we can just round this to approximately, say, 11 days. Approximately 11 days. So all of this was to say that your account will double in, you can either say it'll double in 13.8629 years, or you could say that it's equal to, or you could say that it will double in 13 years, 10 months, and 11 days. 10 months and 11 days. That sounds a little bit better than 13.8629 years, right? 13 years, 10 months, 11 days. Okay, let's double check what the author did. Same thing I did, I think. Yep, we placed it all into here, equals to 10,000. Simplified this, logs to both sides. They also used log base 10. You could have also used log base e. And 14.04. So the money will double in 14.04 years. And over here, yeah, same deal.